All right, Unit 4, Lesson 2, homework. We introduced the logarithm function, natural log function, whose tangent slope generator is 1 over x. It's important that the log function, the log function only exists for x is bigger than 0, so this is 1 over x, but just for x is bigger than 0. It's important to understand when we have a chain or when we don't have a chain. G and H are not chains, but F and R are chains. And whenever we have a chain, our outside is now the log of function. The inside is whatever's inside the log function. And the derivative of log x is 1 over x. The derivative of log parentheses would be like 1 over parentheses. Derivative of x, 2x is 2. Now watch what happens when we multiply the derivatives of these composed functions. We have 1 over times 2. It's 1 over 2x times 2. The 2's will cancel. You end up with just 1 over x. Okay? Let's see with R. Since this is a composition, I'll do this second. Outside is the log function, and the inside is the x squared function. Derivative of the outside, 1 over. Derivative of the inside, 2x. So let's see. Would that be any different than the previous one? Ends up being r prime of x would be 1 over x squared times 2x. You could write that as 2x over x squared, but you could write that as 2 over x, which is probably what you would want to do. Once we have x log x, now we have a product. So remembering the product rule, got the derivative of x times log x plus the derivative of log x times x. And that could be simplified to be log x plus x. Log x plus 1. Here's a quotient, so use the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. I'd simplify that to be 1 minus log x over x squared. This is a good one. This is log x quantity cubed. So this is a chain, but the outside is the cubed. The inside is the log x. Let's see what happens. I have 3 stuff squared, 1 over x. And prime would be 3 log x squared times 1 over x. So maybe to make it look nicer, 3 log x squared over x. Then outside, inside. Now the outside's back to being a log. The inside is 4 minus 3x squared. I got 1 over. I got negative 6x n prime. 1 over 4 minus 3x squared times negative 6x. Okay, a little higher order derivatives. Gonna have to use chain rule. You can either leave the 1/2 out or just put it into the outside. The derivative would be just stuff to the first power. It's like 2 times 1/2 stuff to the first power. And then the log x, its derivative 1 over x. So let's see. F prime, the first derivative, would be log x over x. Right? So this ends up being log x to the first times 1 over x, which is log x over x. And then for the second derivative, we already did the derivative of log x over x, and ended up being 1 minus log x over x squared. Let's find the third derivative given the first derivative. This is very important to remember. This stands for like f prime, the first derivative. So if I take the derivative, I get the second derivative. Now both of these are chains. Now watch this. Derivative of sine 2x. It's got an outside and inside. Outside is a sine, inside is a 2x. It'd be cos 2x times 2. So cos 2x times 2 minus, here the outside is the log function, the inside is the 3x. Derivative of the outside 1 over, derivative of 3x 3. That's 1 over 3x times 3, which is just 1 over x. For the next derivative, the third derivative would be the derivative of the second derivative. I'd have the same idea with cosine 2x times 2. I'd have negative sine 2x times 2 times this 2 turns into negative 4 sine 2x. Then the derivative of 1 over x. The easiest way to take the derivative of 1 over x is not using the quotient rule, but rather rewriting and using the power rule. So I have negative 1x to the negative second using the power rule. That negative 1 and that negative cancel. So x to the negative second turns into that. Okay. Quick to find the value, e to the log, remembering that e to the log x is x, and log of e to the x is x. So e to the log 3 is just 3. That's easy. But e to the negative log 3 is not negative 3. We think it is, but that's not right. We would instead rewrite it as a power to a power. When I write things as a power to a power, it's like when you do that, you can multiply the powers together to give you the negative log 3. So this is actually 3 to the negative first, which actually is 1/3. The next one I'll skip, I'll come back to it. The log of e is just 1. This is e to the first, so this is just 1. Whereas 1 over e can be written as e to the negative first, which is negative 1. What about the log of 1? It can be written as log of e to the 0. That's just 0. We need to be able to understand all of these values and get them. To some piecewise functions. So for these first two, we're making sure that the function is continuous. So the first piece just needs to meet up with the second piece, where the first piece stops using x's when the second piece starts using x's. So we're focusing at 1. So my first guy at 1 needs to equal my second guy at 1. b minus 3 equals 4 log 1. The log of 1, you need to know, is 0. b equals 3. Not bad. Ooh, now we're looking at x equals e. Okay, so f little 1 needs to meet up with f little 2 at e. So I got 2a over e minus 3 has to equal 4 log e plus 2. Well, the e's cancel here. I get 2a minus 3 equals, the log of e is just 1. 4 plus 2, which is 6. So 2a minus 3 equals 6. Add 3 divided by 2. Okay. One more. Another continuous one. Okay. This one with e to the x and log 3. Okay. So first one needs to meet up with the second one at log 3. F little 1 at log 3 needs to meet up with f little 2 at log 3. Got e to the log 3 equals 4 over log 3 times log 3 plus 2. E to the log 3 is, there's no a or b here. Put an a here. There we go. 3a equals 6. A is 2. So my bad. All right, switching gears. Now we need to make sure the function is differentiable. Remember, from back in Unit 2, to ensure differentiability, we need to be continuous, and we can't have any sharp points. To ensure the function is continuous, I need the first piece and the second piece to meet up, just like I was doing. B minus 3 equals a log 1. I get b is equal to 3, because log 1 is 0. All right, no sharp points. That means the functions need to meet up with each other at 1 so that the slopes are nice and smooth. So I can't have a slope that's, different from another slope, or else it's going to be a sharp point. So remember this, we need the tangent slopes. F little 1 prime has to equal f little 2 prime at 1. F little 1 prime is 2. I already know what b is, but I can figure that out. 2bx is the tangent slope generator for bx squared minus 3. The tangent slope generator for a log x would be a is a constant. Derivative of log x is 1 over x, so it would be a over x. Now, plugging in 1 and 3, I get 6 equals a. And I'm done. 1 for x. 3 for b. Let's try this one. Let's make sure we're continuous. A minus 2 equals b log 1. A equals 2. Great. No sharp points. Derivatives at 1 need to equal each other. A is the derivative of ax minus 2 equals. Okay, so b log 3x minus 2. The outside is the log, the inside is the 3x minus 2. Derivative of the outside 1 over derivative of the inside 3. The b can stay in front or up top. So we got b over 3x minus 2 times 3. That's good. That's the derivative of b log 3x minus 2. This, when a equals 2 and when x equals 1, is what we need to figure out. So I get 3b over 1 equals 2. B is equal to 2/3. Okay. All right, some function analysis. When is negative x log x increasing? It's increasing when its derivative is positive. So I'll have to find the derivative, find the zeros. Get negative log x minus 1. Set that equal to 0. Okay, I'll add 1. Divided by negative 1, I get log x has to equal negative 1. I need to be prepared to solve this. I'll take e to the power of both sides to get x equals e to the negative first. Great, 1 over e. I will then, understanding that since it's a log function, I'm going to start at 0 when I analyze my f primes. I get e to the negative first, right here. And I need to use test points. We talked about in class, test points for derivatives that involve the log function should involve an e to a power. So example, e squared is a great test point. E is a great test point. E to another negative number, e to the negative third would be in between 0 and e to the negative first. If I plugged in, let's say e squared, I'd get negative log e squared minus 1. So that's negative 2 minus 1. That'd be negative 3. That'd be a negative. If I plugged in e to the negative third, it'd be negative log e to the negative third minus 1. That'd be negative 3 minus 1. That'd be 3 minus 1. That'd be a positive 2. So f is increasing from 0 till 1 over e. Okay, that probably is tricky for you, which is why we need to practice. When is this function increasing in concave down? We're going to assume that it's for x is greater than 0 because it's the log function. So we already talked about this function, its derivative, and then its second derivative. But if you need to recall, go back to earlier in the homework for the first and the second derivative of 1/2 log x. Yep. And then the derivative of the top times the bottom is 1 minus the derivative of the bottom times the top minus log x over x squared. All right. I need to find the zeros of both of these. Or I need to see when it's undefined. Now, immediately, the bottom set equal to 0 would be when it's undefined, but since it's a log function, we're not even starting at 0. We're starting with x is bigger than 0. So it actually kind of keep that into play, but I don't have to look to the left of it. Instead, I need to figure out when the top equals 0. Log x equals 0, and 1 minus log x equals 0. Both of these are solvable. The first one, I would take e to the power, get x equals 1. Okay. Second one, subtract 1 divided by negative 1. Log x equals 1, e to the power. E to the log x is just x. X equals e. So for my first derivative and for my second derivative, I have my possible sign change locations. 0, interesting, is a starting point. 1 for f prime, e for f double prime, knowing e is like 2.717. Now plugging test points into f prime and f double prime. Okay. Test points would have to involve things with e, like e squared or e to the negative first. I'd have log e squared over e squared. Log e squared is 2. 2 over e squared, positive. log e to the negative first over e to the negative first. That would be negative 1 over e, so that'd be negative e. That'd be a negative. Second derivative. I could plug in 1, or e to the 0. That's a good one to use. 1 minus 0 over the bottom is squared, so it's going to be positive. This will end up being positive. And something like e squared, 1 minus log e squared. Again, the bottom is going to be positive because it's something being squared. So that's 1 minus 2. That's a negative over a positive. F is increasing when f prime is positive. F is concave down when f double prime is negative. So when are they both, when is this positive, when is this negative? That's from e to infinity, or x is bigger than e. Increasing concave up from 1 to e. All right, that's f prime. When is f increasing? All right, f is increasing when f prime is positive. F prime is positive. Find the zeros first. E to the power. Get x minus 3 equals 1. X is equal to 4. Here's my f prime. Assuming we're starting to the right of 3, because you can't have the log of 0. I mean, it's tricky because it's like x minus 3. You could think of this as like 3 plus e. That end up being a positive because it'd be the log of 3 plus e minus 3, which would be the log of 3. That's a positive. Here, it'd be like 3 plus 1 over e. I know that's going to be in between 3 and 4. Be the log of 3 plus e to the negative first minus 3. Log of e to the negative first would be negative 1. So that's a negative. Okay. Let's look at f double prime. I get 1 over x minus 3 times 1. We probably would be starting at 3 anyways. Anything to the right of 3 is positive. So f is increasing for x is bigger than 4. F is never concave down. Okay, same deal. I'm given f prime, finding when f is decreasing and concave up. Very similar to the previous one where we're going to have to kind of manipulate some numbers with e's to do some analysis. I'll start with setting this equal to 0. E to the both sides is 2x minus 5 equals 1. Add 5 divided by 2. So I'd get 3. I mean, since this is f prime, maybe the original function actually does exist to the left of 3. maybe I should be thinking about no, because the derivative wouldn't exist at 2 or 1. It'd be the log of a negative, so I would be starting at 3. So that's fine. This one I would be starting at like 5 halves. Because you can't take the log of anything that is negative or 0. I mean, what would you plug in? Again, I'd plug in like 3 plus log e. That'd be 2 times 3 plus log e. It'd be no, I'd probably plug in 5 halves plus multiples of e. So like here, I'll walk you through this one. 5 halves plus e cubed. I know 5 halves plus e cubed is definitely bigger than 3. Watch. You'd have the log of 5 halves plus e cubed times 5 halves. Sorry, 2 times 5 halves plus e cubed minus 5, which is log of 5 plus 2e cubed minus 5, which is the log of 2e cubed, which is not 6. There's a product out there, or there's a property out there that says it's the log 2 plus the log of e cubed, and that's telling us that that's going to be a positive. And that's going to be the negative. This is a little bit beyond the sign analysis checking that you would be expected to do. What I would recommend is like make sure you're good with this guy and this guy, not necessarily these two. I can tell you it'll be positive and negative like the last one, and then the second derivative is 2 over 2x minus 5. 5 halves would be the guy, but we wouldn't talk about anything to the left of it. If I plug in anything like that, when we are decreasing and concave up, it would be from 5 halves to 3. When f prime is negative, f double prime is positive. Okay, these last two, not as important as these two. Okay. Finishing off with some table problems. Just remember your derivative rules. If I got an outside and inside, I got the log as the outside and f of x as the inside, what would my derivatives look like? It'd be 1 over times f prime of x. So g prime would be 1 over f of x times f prime of x. You want to find g prime of 1. F prime of 1 is negative 1. F of 1 is 3. Here, I have a product, so I need to use my product rule. Derivative of the first times the second, plus the derivative of the second, times the first. Plugging in e, f prime of e, which is negative 3, times the log of e, which is 1, plus 1 over e. F of e is 2, so negative 3 plus 2 over e. H prime of E. All right, that's it. Sorry about these two, a little funky with the sign checking, but there are ways to do it. These are the ones, this guy, that we really need to know how to do, as well as the piecewise functions, and of course all the derivative rules. All right, thank you.